Okay, so this next one here is something that definitely seems like a mystery. Was it yesterday? No, 2 days ago, I recorded the actual lecture for the course these are supplemental materials for, and talked about this and used the standard notation, and it looked mysterious, and I know what it is doing. So definitely wanted to do something in this removing the mystery about programming in machine language. And I already came out abbreviated. So programming in machine language. So we don't have the fancy, all the words put together and reorganize things to match the way humans normally do stuff, like the high-level languages. Don't even have the words that show up in assembly language. We're going to write ones and zeros, which is the first thing we're going to address is we don't do this. We don't go to open a text editor and type 101010. That's not even the way we write it when we program it. But that's what always shows up in computers, and it makes it look even more mysterious and strange. So let's jump into this. I guess the keynote is this is really more of an electrical engineering thing. We're working directly on the machine. So let's get started with this. Okay, so as you probably could figure out without the next sentence I'm going to say, the examples of this can get very complicated very quickly. So I put together a fairly trivial example. Basically a clock signal. I used a 555 timer. That's a timer IC. So it's a little integrated circuit that if we wire it up in a certain order, wire it up in a certain way, we go to a steady on-off pulse. So I put together one of those to be one of our values in the code we're programming this little device with. A very trivial example, but hopefully the concepts are all carried across here, and you can see how these basic concepts can expand out. So that's like a clock. That's just telling us things are, a steady signal of off and on. So just a steady pulse to synchronize everything. And to figure that out, how quickly it's going, I use this formula. The frequency is approximately 1.44 divided by an RC time constant. The video in this playlist about touchscreens goes over RC filters. But for our purposes here, there's a way we can put a resistor and capacitor together and create a delay. So set up that delay, plugged in this formula. I plugged in some numbers, figured out what would give me about a second, and then found some pieces that were close to that. So basically this is a signal that's going to flash on and off. And we're not going to go to a text editor and write 1001001. We're not going to write the code this way. And actually, this isn't even how we think about it when we put it together. This is actually orthogonal to what we think about when we're programming in machine language. But this is what always shows up in textbooks and online reference material and things, and makes it look a little bit confusing. We don't just go type a bunch of ones and zeros to pass in our code. That is utterly confusing, and that is not even what we think about. I'll show what we think about here in a second, or I'll show where that comes from in a second. What we think about is what each one's doing. So this is just a steady clock signal. So it's going to be off for about a second, then on for about a second, then off, then on, off, on, off, on. Did I get an even number here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So I can split that right about here. Make a little mark to tell where halfway is. So that is the first part. And so we'll call a low spot a 0, and a high spot of 1. I guess I can label them over here. So we have a 0 or 1 from that integrated circuit sending out a steady clock signal. So that'll be the first bit in the code we're putting together for this example. And I put together a trivial example, so all we're going to do is flash some lights. There's a red LED, a green LED, a timer circuit, and a toggle switch. So if the toggle switch is one way, the green LED is going to flash. If the toggle switch is the other way, the red LED is going to flash. And we're going to program this machine in machine language and go over all the steps for that. This is the first part, a clock to synchronize everything, just a steady on-off pulse. I use this formula to approximate a 1 second flash. So on for a second, off for a second. And kind of trivial, but the easiest expansion on this might be a stepper motor running the conveyor belt. If the toggle switch is one way, it's moving forward. Stepping forward every second, it clicks forward. If the toggle switch is the other way, every second it steps backward. So that would be a very common use that is almost identical to what we're doing here. But electrical stuff, these concepts expand up very easily. So the trivial examples in electricity should expand quite easily, and you could leave that to motors or any other type of device and kind of see what's going on. But our first part is we get a 1 or a 0 from this 555 timer IC to create a clock pulse. So the next part is the next bit in our code, programming in machine language. And for this trivial example, I just set up a 2-bit code to determine an output. But with electrical stuff, is really, this is electrical engineering. This isn't necessarily computer programming. You wouldn't program a computer like this. With electrical stuff, there's a lot less going on. It's really a much simpler process to work with. So expanding it is just repeating the same thing we already did. Unlike actual computer programming with a high-level language, expanding it, we might need more information, more knowledge in order to expand it. But, with electrical engineering, from the electrical engineering aspect, we have already seen everything our pieces can do. They can be off or they can be on. And then we just combine them. So we need some sort of combination. I'm going to use an AND for this example, which is another big difference between programming in machine language and programming in a high-level language, right? In regular programming language, we're probably going to write a couple ampersands. Or maybe we'll write 1 ampersand for a bitwise AND, which is kind of closer to what we're doing here, but write those symbols or actually write the word AND. But we only have 1s and 0s. And we already assigned the meaning to both of them. So we don't have another symbol we can use for AND. This is an electrical engineering thing, not necessarily a computer programming thing. So I'm going to put brackets around this because for our AND, that is just how we wire it up. We just wire it up, hook the components up as an AND. So that leads into that point. The machine language is specific to the machine it's on. We can't take machine language, the code from one machine, and put it on another machine and expect it to do the same thing. It's very precise to the machine because it's based on how the electrical components are wired together. So the next piece in our input is a toggle switch. And again, it could be off or on, just 2 states. So it's either going to be off, come up, or on. So again, a 0 or a 1. But as we think about this, 0 and 1 aren't going to be helpful. So as we're planning out and putting this together, I'm just going to put some other labels. I'll say a 0 is a green, and 1 is a red. That'll help with putting this together. So that's our inputs. So our options on an input, truth table over here. So either a 555, a toggle, or an LED. So our only options for our input code are going to be off or on. So either the 555 is either off or on, and at any given point, that toggle switch is also going to have a state. So it's either going to be off or on at every point in time. So that's our inputs. So now let's set up the LEDs, the outputs. Okay, so now our LEDs. We have either a red LED or a green LED. Kind of ran out of room. And those we can set to on and off again, right? The LED is either going to be on or off. So we can go back to those terms. In the second one here, well, that 1 and 0, they're almost useless here, right? It's hard to think of them that way. And usually, those terms we usually use, on and off, that's meaningless here because there's no off situation in this line. So I had to find some more useful terms to use for this state of the toggle switch. But again, we represent it with 1s and 0s. So even when we're putting this together, we don't think 1, 0, or we don't think on, off. It changes depending on the situation. So our red and green light. So if our timer is off and our toggle switch is set to the green, well, that's going to be off for red. It's an and situation, and we already hit an off, so we don't even really have to check this one. But the next one, we have on. So on and green, well, that means the LED is going to be off. The red LED is going to be off. Oh, I don't know why I drew that up. And that's going to continue all the way through here. Because it's an and situation, so it's never going to go high while the toggle switch is set to green. So our red will be off that whole way. But then when we get over here, well then the timer's off. We already hit an off. We don't even need to check the and. It's going to be off. Off and on is off. But the next one, on and red, that's going to be on. Again, off. Then we go back to that on and red again. It kind of continues like that. And this is what we think about, how we think about this when we're putting together things in machine language. So I guess we can finish up this last one. For the green LED, well, when the toggle switch is red, that's going to be off that whole time. So if the switch is set to red, there's no way we're going to get a green out of it. But over here, we'll have the same thing. We have and. So off and, well, it's and we already hit an off, so that's going to be off. But on and green, that'll turn that one on. Then off, then on, off, on, then back to that off there. I got a little out of order there, but hopefully you can see kind of what's going on there. I guess I should do two outputs, an R and a G. So here is our machine language. And notice, do I have another color here? Here's red. Notice it goes this way. So it's orthogonal to the way we think about it when we're putting it together. Is here a 0, 0, that's going to produce a 0, 0. So that's the top row here, 0, 0. Then this next block, 1 on the 555, a 0 on the toggle is going to produce a 0, 1. So that is here. 1, 0 produces 0, 1. What else do we have? I guess the next different one is over here. So a 0 and a 1, we're going to produce a 0 and a 0. 0, 1, give us a 0, 0. And a 1 and 1 give us a 1, 0. So there's our truth table. So this is what, whenever you see reference material mentioning machine language, they just talk about the truth table. And there's big chunks of it missing, right? We're missing our logic entirely because there's no symbol representing it. That's done entirely in hooking up the electronic components. And not only that, this is completely orthogonal. We're putting this together, we're thinking this way. But we read our code from it is read that way. So that's how putting machine language together works. Let's go look at this example just to see this. And expanding it is quite simple because we just do this again. We've already seen all the parts. We might have an or situation or a not situation to work it. We have those gates as well. The different logic gates we can put in. But then each one of our components is either going to be on or off. And as time progresses this way, we can build up a code control of what's describing the machine state at every point in time. So that's how programming in machine language works. Let's go look at the example to see this in action real quick. A very trivial example, but this expands a whole lot easier than programming in high-level language. Because programming in high-level language, usually to expand what we're doing, we have to learn more about the language. Whereas we only look at one of the logic gates. We have two more basic ones and some other combinational logic gates. But those are in another video, and we've seen everything that we can do here. So programming in machine language is more of an electrical engineering thing. It's not a computer thing. We wouldn't go through and program our computer this way. The ENIAC machine was done this way. That's why I don't like to count it. I usually like to start with the EDVAC machine, which is more like which started the separation between electrical engineering and computer field. So that's how programming in machine language works. Hopefully this helps remove some of the mystery for it. Let's go look at the example. Okay, so here's this example showing machine language. So what's going on here? Over here, I have a 555 chip that is just an integrated circuit that if we hook it up in a certain way, it'll send out a steady pulse. So I hooked it up, it's called astable mode here. So just made the connections and put in an RC filter, a resistor and capacitor, and I just did a rough approximation. I approximated the math and then found pieces close to what I found from doing the math. So it's approximated twice, but it should be about a second on the flash. The flash on, not necessarily the flash off, but a steady signal pulsing there. And then it's wired up so that timer, the signal from that timer, is in an AND situation with this toggle switch. And then the output is the red or green LED here. A very trivial example, because this can get very complicated very quick, but even this trivial example, if we just replace these LEDs with, say, a stepper motor on a conveyor belt, that would be an almost identical example that would actually do something, because then we could set like reverse or forward so that every second or whatever the conveyor belt would jump forward or jump backwards. And that's a typical use of where machine language would show up. Typically that would be done on a PLC, so we wouldn't do it all from scratch, but this is the basic idea here, just a trivial example showing it. So timer and toggle switch pulled left gives us a red when the timer goes high, and both of them are off when the timer goes low. And if I flip the switch, then timer and toggle switch to the right gives us a green when the timer's high, and both of them are off when the timer's low. So that's just a quick trivial example of how working in machine language works. And unlike high-level language, expanding that is a whole lot easier because we don't need more knowledge to expand that. From that picture I drew on the board where there was the 2 rows for the inputs, to expand that we would just put more input rows and trace the signal through the same way and just build a truth table off of it. And then that truth table kind of shows our machine language. So that's how programming in a machine language works. Hopefully that helped to remove some of the mystery of that. And when I was getting the class lectures ready and went over that part, I know how to do the machine language stuff, but writing it with 1s and 0s on the board and trying to talk about it in that situation, it still seemed mysterious to me. And I know how to do it. So hopefully that helped to clear up some of the mystery of that strange looking machine language you'll see in reference material.